These are mind games. There are no truths here, only their shadows. Can a chair think? It sounds like a joke, a riddle for children, until you pull at the thread and everything begins to unravel. Right now, you're watching something learn to play Pong, and not just play, improve within minutes. At first, you might assume there are living neurons behind it. That would make sense. A few years ago, researchers connected mouse embryo neurons and even neurons grown from human stem cells to a computer. The neurons received signals via electrodes about where the ball was, where it was heading, and sent signals in return, controlling the paddle on screen. But this time, there are no neurons, nothing alive, no circuitry, no algorithms, just material, inert, unthinking, a hydrogel. And yet, it learns. You're watching polyacrylamide hydrogel, the same cheap, squishy stuff we use to purify water, hydrate soil, and strengthen concrete, learning how to play a game. A material, not a brain, not a device, not a simulation, just matter. Nearly all water, and somehow it adapts, it gets better, it behaves. A lifeless blob, mastering a game better than a toddler. Now the question, can a chair think? Suddenly sounds less ridiculous, especially once you define what thinking actually means. If a chair can think, why not the universe? Our research shows that even very simple materials can demonstrate complex and adaptive behavior, the kind we typically associate with living systems or advanced artificial intelligence. Here's what's happening. Researchers discovered that hydrogel exhibits memory. When you apply an electric charge, ions inside the gel begin to move. This ionic movement alters the gel's electrical conductivity. Scientists used this property during the Pong experiment. As the virtual ball moved, some electrodes zapped the gel with current. Others measured how its conductivity shifted in response. Where the conductivity changed, that's where the paddle moved, and within minutes, the gel started to remember those signals. Here's how the researchers explained it. As ions accumulate, their migration slows due to an increasing concentration gradient. Eventually, the ions stop moving, and the electric current peaks. This means the gel's internal ion distribution settles into a stable configuration, one that encodes information about recent game interactions. A temporary memory, like a sponge holding a fingerprint, until a new one presses in. Only here, the next imprint depends on the last one. The past shapes the future. In physics, this is called hysteresis, a lag in response where previous states affect what comes next. Over time, this behavior means the hydrogel gets better at responding. In early trials, the paddle hit the ball half the time, pure chance. But after just 30 minutes, the hit rate climbed to 60%. No code, no training, just repetition and the gel's physical structure adapting through feedback. Sound familiar? The researchers saw a parallel with how brains learn. They cited the theory of free energy, a concept from neuroscience and Bayesian statistics. The brain, according to this model, constantly works to minimize the gap between what it expects and what it perceives. That gap is called free energy. The smaller the gap, the more accurate the brain's predictions, and the more efficiently it learns. Now here's the kicker. Similar predictive behavior may be happening in the hydrogel, not symbolically, but physically. No neurons, no intent, just physics. If a lump of wet polymer can learn, if it can change in response to experience, if the past can shape the present in matter without life, then tell me again, why can't it think? In a recent study, physicists explored how a chaotic mass, made up of units that may or may not be intelligent, it doesn't matter, can spontaneously shift from disorder to order without any conscious guidance or central intelligence. One moment, everyone is moving independently, the next, they're aligned, as if following some unwritten law of nature. Whether it's a crowd, a flock of birds, or a swarm of non-living yet active particles, the transformation is sudden and striking. In our field, researchers of collective motion tend to believe there's a qualitative difference between particles, like atoms and molecules, and biological elements such as cells or organized groups like flocks or crowds. It's thought that their transition from chaos to order happens through fundamentally different mechanisms. But it turns out that's not the case. In fact, the same mathematical principles may apply across the board, from curing diseases to optimizing traffic systems. The key lies in understanding active matter, systems of particles that possess their own internal energy and can self-propel. Schools of fish, cancerous tumors, locust swarms, drones, sperm cells. These are all forms of active matter. Initially, their movements are random and chaotic, but then, without warning, order emerges. Physicists describe this shift as a phase transition, and it's non-linear. It doesn't unfold gradually, but all at once. Think of the sudden color shift in the Belousov-Zhabotsky reaction, or how pendulums on a shared platform slowly synchronize. No central control, no external signal, just physics. So what's the hidden mechanism? The study's authors point to fluctuations, small deviations in movement. Someone in a crowd steps slightly to the left. A bird turns faster than expected. A few particles slow down. From a mathematical point of view, these fluctuations are a kind of noise. When this noise was added to even the best existing models, which had still fallen short, something clicked. Suddenly, the random jostling gave way to spontaneous bursts of order. Like a spark in the dark, a pocket of synchronized movement appears, and then it spreads. The system splits. Part remains chaotic, while a coherent group forms. A flock cutting through the noise, and as more particles join, the order consumes the chaos. Eventually, the entire system moves as one. Then, inevitably, disorder may return, but for a moment, maybe only a moment, there is order so precise, so self-consistent, it almost deserves to be called intelligent, or, with some poetic license, thinking. This may turn out to be the strangest and most unsettling prediction in the history of cosmology, if not all of science. If it's true, then you, the reader of this article, are more likely to be a brief fluctuation in a field of matter and energy, arising randomly somewhere in space, than a human being with a real evolutionary past in a structured, star-filled universe. Your memories and the world you think you see are illusions. Absurd? Maybe, but this bizarre idea, a disembodied, thinking brain spontaneously born out of nowhere, actually reveals something profound about the structure of the universe. Imagine waking up and finding everything gone. No Earth, no sun, no galaxies, just infinite empty space saturated with dark energy. And you? The only thinking entity in existence, a fluke of particles assembled by chance. Your mind, your memories, your sense of self, all illusions created by a temporary fluctuation. Before you, there was nothing, and after, there will be nothing again. If we really were such brains, the probability of observing a universe filled with galaxies and planets would be practically zero. It would be far more likely to wake up alone in a void. This thought experiment, the Boltzmann brain paradox, emerged from a real scientific development, the discovery of the universe's accelerating expansion. Physicists realized that empty space contains a small but persistent amount of energy, dark energy. If this acceleration continues indefinitely, the universe will evolve into a cold, dark emptiness, filled only with quantum vacuum fluctuations. This hypothetical future is called de Sitter space, named after astronomer Willem de Sitter. And here's where things get weird. According to quantum mechanics, even empty space experiences random fluctuations, brief, spontaneous shifts in fields and particles. Most are tiny and meaningless, but larger ones are theoretically possible. In the early 2000s, cosmologist Andreas Albrecht proposed that in a universe like ours, these rare but inevitable fluctuations could produce boltzmann brains, disembodied minds, spontaneously arising from chaos. At first, it seemed like a joke, a tongue-in-cheek side effect of quantum physics. But the problem is real. If boltzmann brains are more probable than evolved observers like us, then most observers in the universe should be them, and we shouldn't exist at all. Which means either something's wrong with our understanding of cosmology, or something far stranger is going on. If our universe is heading toward a stable de Sitter space-time, then boltzmann brains will eventually outnumber normal observers, no matter how low the nucleation rate of boltzmann brains may be. In other words, if our current cosmological models are correct, then the typical observer in the universe shouldn't be someone like us. It should be a boltzmann brain, a fleeting, self-aware fluctuation that spontaneously appears in an otherwise empty universe. But here's the problem. We know we're not boltzmann brains. We have histories. We evolved through biological processes over billions of years in a structured, star-filled cosmos. That creates a paradox. According to the math, we shouldn't exist as we are. Worse still, if you were a boltzmann brain, the chances of seeing a structured universe full of stars, galaxies, and planets would be essentially zero. You'd be far more likely to wake up, floating in an empty void with random thoughts and false memories. No universe around you at all. Yet here we are, staring into an elegant and ordered cosmos. So either our understanding of the universe is wrong, or we're missing something fundamental. To resolve this contradiction, physicists had to introduce bold new assumptions, backed by extremely complex mathematical frameworks. One such idea is vacuum decay, the notion that what we consider the vacuum of space isn't stable. Over time, it could tunnel into a lower energy state, abruptly transforming the fabric of reality. If the universe is not eternal, but instead only lasts, say, 20 billion years, then boltzmann brains won't have enough time to emerge in significant numbers. The paradox dissolves. Another possible solution, quantum mechanics, might break down on cosmic scales. We can't yet confirm whether the laws of quantum physics that govern our labs also apply across the vastness of the universe. If those laws behave differently at extreme scales, the kinds of enormous fluctuations needed to produce boltzmann brains may be impossible, even in theory. And the problem of boltzmann brains could be solved by the multiverse theory. Then our universe would be just one of an infinite number of universes with different properties, and we would be in the one where such mega-observers do not arise from quantum fluctuations, but statistically appear in some other universes. And then everything would make sense. Absurd? Maybe, at least to those unfamiliar with the mathematical and philosophical depths of modern theoretical physics. Because once these ideas are translated into everyday language, they seem to lose all traces of common sense. But can we, while looking out at the universe, truly deny the most paradoxical truth of all, that we are the universe observing itself? The surface of the Earth is the shore of the cosmic ocean. Recently, we've waded a little way out, and the water seems inviting. Some part of our being knows this is where we came from. We long to return, and we can. Because the cosmos is also within us. We're made of star stuff. We are a way for the universe to know itself. For astrophysicist and legendary science communicator Carl Sagan, this wasn't just poetic. It was a metaphor for our civilization's evolution during the scientific and technological revolution. But in his time, we lacked the tools to see what we now can. Something astonishingly familiar, a structure that resembles the neural networks in our own brains. It's called the cosmic web, an immense filamentary network of galaxy clusters stretching across the observable universe. The dense threads are clusters of galaxies and gas. The voids between them aren't empty, just less dense regions of matter. What we see isn't a photo or even a stitched-together composite. It's a simulation, a mathematically generated model based on astrophysical measurements and observations, and it's strikingly accurate. New data aligns remarkably well with the predictions of this model. That uncanny resemblance between the cosmic web and the human brain has caught the attention of scientists from two very different worlds, astrophysicists and neurosurgeons, who decided to compare the two systems, not qualitatively, which is currently impossible, but quantitatively. To do this, they used samples from actual brain tissue, taken from the cerebral cortex and cerebellum during tumor removal surgeries. The neurons were stained with special dyes, and the tissue was sliced into ultra-thin layers, each just 4 micrometers thick. For the cosmic web, they simulated a cubic section of the universe 100 megaparsecs across and extracted 12 slices from it, each 25 megaparsecs thick. The images were then analyzed using the same techniques. They examined the spectral density of matter at different scales and performed network analysis to identify key nodes and connections, not just by visual inspection, but with hard data. We are investigating the structural, morphological, network properties, and memory capacity of these two fascinating systems using a quantitative approach. Memory capacity? What kind of memory could clusters of galaxies possibly have? Certainly not the kind found in the human brain or a computer. Not even like the hydrogel experiments, where simple materials began remembering stimuli. right? For the cosmic web, we can use an idea from information theory to estimate how much information is encoded in its three-dimensional structure. In other words, we can calculate and estimate how much information would be needed to fully describe the structure of the cosmic web. After all, the more orderly a system is, the less information is needed to describe it, because the structure implies some kind of logic, which means that it is not necessary to know the exact coordinates of all the particles that make it up. This is called the information capacity of the system, and researchers compared it to how much information all the neurons in the human brain can store, based on about 5 bits per cell. Here, they relied on someone else's research. The comparison is, of course, very tentative, but the authors say, "We want to inspire others to at least look in this direction and, perhaps, find more interesting and profound solutions." So far, researchers have found that the information capacity of the cosmic web and the human brain are surprisingly comparable, at least within this framework. The web contains just over 4 petabytes, while the brain holds an estimated 2.5 petabytes. Of course, these are games of our mind. When our brain looks closely at the universe, it often sees its own reflection. Otherwise, it would probably be more difficult to understand or accept it. This has been the case since ancient times, when we first began to assume that the universe might be intelligent. But with the development of quantum mechanics and information theory, we seem to have enough imagination for more daring conjectures, and the smartest among us, such as theoretical physicist John Wheeler, one of the creators of the first atomic bomb, and scientific leaders of quantum mechanics such as Hugh Everett and Richard Feynman, are taking the next step. What if the universe is not intelligent, but acts intelligently as a perfectly coordinated automaton, a machine that does not understand what it is doing? It has no desires, aspirations, fears, or emotions, but its very organization is such that it creates something at a fundamental level, which allows something to exist from nothing. Perhaps calculations are taking place at the most basic level of reality, which give rise to physical reality itself, the laws of physics. Here one wants to ask, any machine, even a hydrogel playing Pong, was created by someone. So who created the machine that created the universe? But Wheeler, the man thanks to whom we use the very concept of black holes, such a prominent and authoritative physicist, says exactly the opposite about the universe. It is worth trying to think of it as an alpha and omega machine that calculates and generates itself. But if it creates the foundation of foundations, the fabric of reality, what then is this machine itself made of? Is it like God in some philosophical and religious concepts outside this world, transcendent? Every physical quantity, every it, acquires its ultimate meaning from bits, binary yes-no indications. Wheeler proposes a hypothesis in which the basis of reality is information, and it, according to Wheeler, is more fundamental than matter or energy. Information, as the physicist explains, is the answers to the question yes or no are conditional, not literally ones and zeros. He offers this line of thought, looking at the oddities of quantum mechanics. Take an electron. We can't say exactly where it is or even if it has a defined position until we ask. That is, until we measure it. And when we do, we get a simple answer. Yes, it's here, or no, it's not. This applies to all quantum properties. Until measured, they exist in superposition, all possible states at once. Measurement collapses this uncertainty into a definite outcome. And that outcome, that binary response, is a bit of information. According to Wheeler, this is how reality is built, bit by bit. And here it is very easy to slip up because reality, it turns out, depends on our perception. After all, if we do not interact with something, does that mean it does not exist? This is an ancient philosophical riddle. Can you hear a tree falling in the forest if no one is around? But Wheeler isn't proposing mysticism. He's a physicist, and he doesn't claim that a chair stops existing when you stop looking at it. Macroscopic objects are constantly interacting with their environment. These interactions disrupt quantum uncertainty, even without a conscious observer. So yes, the chair exists. But Wheeler wants us to rethink how we define that existence. Let's try to look at reality not in terms of what exists on its own, but in terms of the information we can obtain and how that information fits together. In other words, instead of imagining reality as a collection of self-contained objects, atoms, particles, things, we should view it as a network of interactions, a constant exchange of information. It's the same idea we saw in the study of flocks and swarms. Order emerges not from external commands, but from local interactions between neighboring units. Chaos becomes coherence. Disorder transforms into structure. From mindless motion, meaning. From randomness, form. That's not intelligence, but it's intelligent behavior without intelligence, computation without a computer, learning without a learner. So, can a chair think? Let us know what you think in the comments. After all, these are mind games. There are no truths here, only their shadows. Thank you to everyone who supports with likes, comments, and shares. It really matters. See you soon.